The increasing amount of technology we rely on in everyday life makes portable energy sources essential to our world today. We can power our cell phones and laptops with lithium-ion batteries, run flashlights from alkaline ones, and many of our watches depend on batteries constructed with silver oxide. This one, though, may be the most important of them all. Now, I know it seems a clunky, old-fashioned thing. It was invented in the 19th century, but it still makes our world move by starting our cars, motorcycles, and trucks. No wonder it's the best-selling battery. If you understand how this battery operates, you can grasp the principles underlying any of the newer ones and even see why no single type of battery can be used in all applications. Let's take a look inside. The first thing to note about this motorcycle battery is that it's heavy. That's because it's tightly packed with lead and lead oxide sheets, both of which are very dense. This is a cell from an identical battery, and you can see the lead, and underneath this, the lead oxide. They alternate throughout the interior. So let me show you how they store electricity using just 2 plates. So I have here a lead plate and a lead oxide plate from the battery, and the sulfuric acid. And now watch what happens when I connect the leads. The LED lights up. A current flows from the lead oxide cathode to the lead anode. The lead gives up electrons which the lead oxide accepts. This exchange turns both plates into solid lead sulfate. Now, let me measure the voltage difference between the 2 leads. And you can see that it's about 2 volts, which means that to make this 12-volt battery, 6 cells are linked in series to make up the 12 volts. So that's the basic electrochemical reaction. Now let's look at how you engineer a battery. We want a battery to have a high density of either energy or power, and that difference being that batteries with a high energy density can store large amounts of energy and release it reliably over long periods of time, whereas batteries with a high power density release large amounts of energy quickly. This battery was designed with power in mind because we need a burst of nearly 400 amps to start a motorcycle. To save space, we need to pack the plates in here tightly, but in order to ensure that the electron transfer takes place through the terminals, the plates are mechanically separated by these permeable layers. Now, let me show you 2 plates from a discharge battery so you can see the effect of a deep discharge of a battery. If we look at these 2 plates, we can see the effect of a long-term discharge. This light coating here is lead sulfate. That explains why if you run a car battery to 0 charge a few times, you're likely to kill it. As the battery discharges, lead sulfate cakes the space between the plates. If too much builds up, you'll never be able to recharge the battery. This highlights how every different application needs a different type of battery. You see, with most engineered objects, there are going to be trade-offs, giving away some characteristics you want to gain others that you must have. Indeed, the toughest part of engineering often ends up being balancing the trade-offs in a design. For example, a car battery does a great job starting a vehicle, but not running one, like an electric car. Nor is it a good candidate to store energy from solar panels in a house. There, we harvest energy from the sun, charge up the batteries, and then use the stored energy in a variety of ways until the batteries die, and then recharge them with the sun's energy. For this use, you would use what is called a deep cycle battery. As the name implies, this battery's capacity can be largely used and then recharged easily. To convert an SLI battery, like used to start a motorcycle or a car, into a deep cycle battery, we do 3 things. We use thicker electrodes to increase energy density, space them further apart so lead sulfate debris can fall off of them, and add room below where that debris can accumulate. The trade-off is that it's larger, heavier, and gives off a lower current than a car battery. It would seem that we'd want to get rid of the lead-acid battery. It poses a significant environmental risk if disposed of improperly. We still have the 19th century lead-acid battery because of what nature has handed us. Plentiful electrode materials, lead and lead oxide, both very high in conductivity. Once we arrange these materials correctly, we have a cheap battery with a high power density. No other materials found in nature meet these criteria so well, which means that with current technology, it is extremely difficult to overcome this barrier. That's why 19th century technology is still the go-to for starting our cars. I'm Bill Hammack, the Engineer Guy. This video is based on a chapter in the book, 8 Amazing Engineering Stories. The chapter features more information about this subject. Learn more about the book at the address below.